configuration with 2 hots and 1 neutral is indeed considered single-phase power. The reason for this lies in the transformer windings. These windings are designed and connected in a specific manner that ensures the 2 hot conductors are in phase with each other. In other words, their voltage waveforms rise and fall together, as opposed to being offset as they would be in a multi-phase system. Think of it like this: imagine 2 people pushing a swing. If they push at the same time in the same direction, that is analogous to single phase. If they push at different times, that's more like multi-phase. Now let's discuss Article 210.8, which is relevant to this configuration. This article pertains to ground fault circuit interrupter protection for personnel. However, it does not directly address the sizing of the neutral conductor in a single-phase system with 2 hots and 1 neutral. What is critical is understanding the neutral conductor's role and ensuring it is appropriately sized according to other applicable articles within the National Electrical Code, specifically articles concerning neutral load calculations. The neutral conductor in a single-phase system with 2 hots and a neutral carrier is the unbalanced current. Unbalanced current occurs when the loads connected to each hot leg are not equal. For example, if one hot leg is powering a 10 amp load and the other is powering a 5 amp load, the neutral conductor will carry 5 amps back to the source. The larger the imbalance, the more current the neutral will carry. Therefore, it's important to understand how to calculate the neutral load. Firstly, determine the load on each hot conductor. This is typically done by adding up the amperage of all the devices connected to each hot leg. Secondly, identify any loads that are not considered continuous. Continuous loads are defined as loads that operate for 3 hours or more at a time. Thirdly, for non-continuous loads, the neutral load is simply the difference between the loads and the 2 hot conductors. Fourthly, for continuous loads, you need to factor in a demand factor. The demand factor is a percentage that represents the amount of current that is likely to be flowing at any given time. The demand factor will vary depending on the type of load and the application. Fifthly, once you have determined the demand factor, you can calculate the neutral load for continuous loads by multiplying the load on each hot conductor by the demand factor and then finding the difference between the two. Sixthly, add the neutral load for non-continuous loads and the neutral load for continuous loads to get the total neutral load. Now let's talk about sizing the neutral conductor. The neutral conductor must be sized to carry the calculated neutral load. Article 220.61 provides guidance on calculating the neutral conductor size for household ranges and electric clothes dryers. It allows for a demand factor to be applied to the neutral load calculation. Article 310.15 and associated tables, such as Table 310.15b16, dictate the allowable ampacities of conductors based on their size, installation type, and installation conditions. You must select a conductor size with an ampacity equal to or greater than the calculated neutral load. Several factors influence the selection of the correct conductor size. Firstly, the calculated neutral load is determined by Article 220. Secondly, the conductor's insulation type, which affects its temperature rating and ampacity. Thirdly, the installation method, as different methods e.g. in conduit, direct burial, free air have different heat dissipation characteristics affecting ampacity. Fourthly, ambient temperature, as higher temperatures reduce the ampacity of conductors. And fifthly, the number of current carrying conductors in a raceway or cable, as this can also reduce ampacity due to heat buildup. Now let's dive into some additional considerations for neutral conductor sizing. Firstly, voltage drop. While the NEC focuses on ampacity to prevent overheating, voltage drop is also crucial for proper equipment operation. Excessive voltage drop can cause lights to dim, motors to run inefficiently, and electronic equipment to malfunction. Secondly, future expansion. Consider whether the electrical system is likely to be expanded in the future. If so, it may be wise to oversize the neutral conductor to accommodate future loads. Thirdly, harmonic currents. Nonlinear loads, such as electronic devices, can generate harmonic currents that flow in the neutral conductor. These harmonic currents can increase the neutral load and may require a larger neutral conductor. Fourthly, continuous loads. Pay close attention to continuous loads, as they require a higher ampacity rating for the neutral conductor. Fifthly, local codes and regulations. Always check with the local electrical inspector to ensure that the installation complies with all applicable codes and regulations. Now let's explore some common misconceptions about neutral conductors. Firstly, the neutral conductor is not always a ground. While the neutral conductor is connected to ground at the service entrance, it is not the same as the equipment grounding conductor. The equipment grounding conductor is a separate conductor that is used to provide a path for fault current back to the source. Secondly, a neutral conductor does not always carry current. In a perfectly balanced three-phase system, the neutral conductor will carry no current. However, in most real-world installations, there will always be some amount of unbalanced current flowing in the neutral conductor. Thirdly, the neutral conductor can be smaller than the ungrounded conductors. In some cases, the NEC allows the neutral conductor to be smaller than the ungrounded conductors, but only if certain conditions are met, such as the neutral load being less than the ungrounded load and the installation complying with specific code requirements. Fourthly, the neutral conductor is always white or grey. While white or grey are the standard colors for neutral conductors, other colors may be used in certain situations, such as when the neutral conductor is larger than number 6 American wire gauge. In these cases, the conductor must be marked with white or grey tape at all termination points. Let's consider some practical examples of neutral conductor sizing. Firstly, a single-phase dwelling unit with a 100 amp service. The NEC provides specific guidance on calculating the neutral load for dwelling units, taking into account factors such as the size of the dwelling, the number of appliances, and the heating and cooling systems. Secondly, a commercial building with a mixed load of lighting, receptacles, and HVAC equipment. The neutral load calculation for a commercial building can be more complex, as it requires careful consideration of the different types of loads and their demand factors. Thirdly, an industrial facility with heavy machinery and process equipment. Industrial facilities often have large and complex electrical systems, and the neutral load calculation must be performed by a qualified electrical engineer. Now, let's discuss the importance of proper neutral connections. A loose or corroded neutral connection can cause a variety of problems, including voltage fluctuations, equipment malfunctions, and even fires. Therefore, it is essential to ensure that all neutral connections are tight, clean, and properly torqued. Firstly, use the correct tools. Use a torque wrench to tighten the connections to the manufacturer's specified torque. Secondly, inspect the connections regularly. Check for signs of corrosion or damage, and retighten the connections as needed. Thirdly, use antioxidant compound. Apply an antioxidant compound to the connections to prevent corrosion. Fourthly, avoid over-tightening. Over-tightening the connections can damage the conductors or the terminals. Fifthly, ensure proper grounding. Make sure that the neutral conductor is properly grounded at the service entrance. Let's talk about troubleshooting neutral problems. Firstly, voltage imbalances. A voltage imbalance can be caused by a loose or corroded neutral connection, an overloaded neutral conductor, or a problem with the transformer. Secondly, flickering lights. Flickering lights can be caused by voltage fluctuations due to a loose neutral connection or an overloaded circuit. Thirdly, equipment malfunctions. Equipment malfunctions can be caused by voltage fluctuations or by harmonic currents flowing in the neutral conductor. Fourthly, hot neutral conductors. A hot neutral conductor can be caused by an overloaded neutral conductor or by a loose or corroded connection. Fifthly, buzzing sounds. Buzzing sounds can be caused by loose connections or by harmonic currents flowing in the neutral conductor. To measure neutral current, use a clamp meter. A clamp meter is a non-contact ammeter that can be used to measure the current flowing in a conductor without having to disconnect it. To measure neutral to ground voltage, use a voltmeter. A voltmeter is an instrument that is used to measure the voltage between 2 points. Now, let's consider some advanced topics related to neutral conductors. Firstly, active neutral conductors. Active neutral conductors are used in some advanced power systems to actively control the neutral current. Secondly, harmonic filters. Harmonic filters are used to reduce the amount of harmonic current flowing in the neutral conductor. Thirdly, neutral displacement voltage. Neutral displacement voltage is a voltage that can occur between the neutral conductor and ground in a three-phase system. Finally, it's worth noting that electrical codes and best practices are constantly evolving. Always consult the latest edition of the NEC and other relevant standards for the most up-to-date information. Proper understanding and application of these principles ensure safe and reliable operation of electrical systems. This is particularly true in the case of neutral conductors, which play a vital role in carrying unbalanced currents and providing a stable reference point for voltage.